Okay, what's up guys? Welcome to this tutorial. I am going to be continuing the 2015 supplementary exam. I'm going to be focusing this video on question 5, momentum, energy, and power. Okay, so let's give this question a read. Okay, so we have railway carriage X of mass 21,000 kilograms crashes into the back of a railway carriage Y, which is traveling at the same direction as X on a straight level track. Okay, and then we've got the velocity time graph, which is shown. Okay, so cool stuff, nothing too difficult. Ignore friction forces, cool stuff, and ignore air resistance, cool stuff. Okay, question, let's go into it. Let me make this a bit smaller. And let's get into it. So we can start with question 5.1.1, and it says, calculate the distance traveled by carriage Y between 1 second and 2.4 seconds. Okay, so 1 second is right here, and 2.4 seconds is right here. Okay, and we want to know the distance traveled. Okay, so the distance, okay, so I think I've been over this, but I'm just going to say, so we have SVA, so S stands for displacement, our displacement graph, our velocity graph, and our acceleration graph. To get from a velocity graph to our displacement or our distance, we use the area under the graph. Okay, so we want this area right here. So this is our graph Y, and we want to know the distance traveled between 1 and 2.4 seconds. So we want this distance right here, or this area right here. Okay, so writing it out, we can say that the, let's do it in black, distance is equal to, okay, I'm going to break this down into blocks right there. So it's going to be 2,4 minus 1 times a height of 1 plus, we've got a triangle, which is a half. Our base is exactly the same as it was, 2,4 minus 1 times our height, which is 3 minus 1, which is 2. Okay, and the answer that we get is the following. So we have 2.8 meters. Cool stuff. And that's that. Nice 4 marks. Great stuff. Okay, then it says calculate the magnitude of the change in momentum of a railway carriage X between 1 second and 2.4 seconds. Okay, so the question is, what is the change in momentum? Okay, so change in momentum, okay, so change in momentum is denoted the sign change in P, and it's equal to the mass times the velocity of the final minus the mass times the velocity of the initial. Okay, if we erase what we had here, and let's see. So we wanted at carriage X, so this is going to be our VI, and then at 2.4 seconds, this is going to be our VF. Okay, and we know the mass. Okay, I'm going to group this as well, so I'm going to say that's 21,000. Okay, I've pulled out the mass, so then we just need to take the velocity of the final, which is 2, minus the velocity of the initial, which is 5. Okay, and the answer that we get is minus 63,000 kilograms meters per second. Okay, and there we go. Another 4 marks quite easily. Cool stuff. Then it says calculate the net force experienced by the carriage between 1 second and 2.4 seconds. Okay, so we need to ask ourselves, what is the net force? So 5.1.3 is asking for F net, which is equal to, let's say, MA, using our normal equation. Okay, so we need to figure out what our acceleration is, because we know what our mass is. Okay, so we can put in our mass is equal to 21,000, and our velocity, we can write this as m. Acceleration is defined as the rate of change of velocity, so it's dv over dt, or change in velocity over change in time, which is our gradient. Okay, and we're looking for this gradient right here. So I'm going to take the points 2, so it's going to be 2 minus 5. So that's our change in velocity over our change in time. The value is 2.4 minus 1 second. Okay, and plugging this into our calculator, we get the following answer. Okay, we get minus 45, 1, 2, 3, and it's a force, so it's a Newton. But it asks for, it does ask for the net force experienced, and it's a vector. So what does this minus sign mean? It just means in the backward direction. So I'm just going to say the net F net is equal to 45,000 newtons backwards, or in the opposite direction of travel. Okay, we can say it like that. And there we go, 4 more marks. Great stuff. And then it says, calculate the mass of carriage Y. Okay, so what is this question asking for? It's asking for mass of Y. Okay, so how are we going to work this out? Okay, so an important fact that we know is that the impulse, change in P for the, let's say, change in impulse for X is equal to the change in impulse for Y. Okay, and we know what the change in impulse was. Okay, I'm just going to use the magnitude, so we're going to say it's 63, 1, 2, 3 is equal to, and change in impulse of Y can be written as mass of Y, velocity of final minus velocity of initial. Okay, again, I just want the absolute value, so we're looking for the mass of Y. Okay, then we know the velocity of Y final is going to be, okay, so we're looking at this graph right here. The impulse we're concerned about is in this time step right here. So I'm going to take V final as equaling 3 and V initial is equaling 1. So we're going to have 3 minus 1, which is obviously 2. So My is equal to just half of 63 is equal to 31,500 kilograms. Okay, and that is our final answer. Cool stuff. That is our final answer there. That is our final answer there. That is our final answer there. And yet again, we have 4 marks. Quite nice, actually. Okay, so now let's get into something a bit more interesting. Let's see if I can. Okay, we'll just work. Let's see if I can insert some space for myself. No, it's not really. Oh, it will actually let me. Cool stuff. I've got a bit more space. Okay, so now we get to 5.2.1. Okay, after the collision, railway carriage X of that mass is taken to the repair yard, where it is pulled up a track of the following inclination to the horizontal. It is pulled at a speed, so we can say that the velocity that it's being traveled is a constant 1.4 meters per second, and I'm just going to put that. Sometimes it's good to annotate what's actually happening. Okay, and the height here given to us is 8 meters. Okay, cool stuff. So what I'm going to actually first start off doing is getting this length right here. I don't know if it's going to be useful, but it might be, so I'm just going to get that length. Okay, how do we do that? Okay, so we know that sine of 20, okay, sine of 20 is equal to our opposite, 8 meters over our hypotenuse. Okay, so let's say, okay, so the value of that is going to be equal to 23 meters, 39 meters. Okay, I don't know if that's going to be useful, but it is a piece of information that I can get very easily, so I might as well just do it, and it takes me very little time. Okay, so let's start off with question 5.2.1. Okay, question 5.1. It says, calculate the gain in gravitational potential energy of the carriage when it's moved from the bottom to the top. Okay, so that's very easy. So what's it asking for? The gain in gravitational potential energy, which is EP, and it's given the formula mgh. Okay, we know what G is, we know what M is, and we know what H is. Okay, mass is 21,123,000, 9.8. Let's use 9.8, and the height is 8 meters. Okay, and the value that is given is the following: 1,646,400. And what joules are we using? What units are we using? We're using joules. Okay, and we can also have written this in as 1.65 times 10 to the 6 joules. Either one of them is correct because it means exactly the same thing, and we get 3 marks right there. Okay, then it says calculate the magnitude of the force applied by the cables if the let's start that again. Calculate the magnitude of the force applied by the cable to the carriage if the frictional force between the carriage and the track is a constant 21,000 newtons. Okay, so 5.2.2. Immediately when I'm working with forces, all I want to do is draw a free body diagram. So I'm going to start off by doing that. So right here we have our weight. Okay, and that's equal to mg. We know that. Okay, then we have the force applied, which is what we're looking for, and we have force of friction. So we write that as force friction, which is equal to 21,000 newtons. Okay, we can also write mg as equaling 205,800 newtons. Okay, so what the first question we really need to ask ourselves is, what plane are we working in? Okay, usually we can set coordinate systems quite easily like this, and we can say this is the x coordinate system and this is the y coordinate system. Okay, in this case that doesn't really help, so we set up coordinate systems that look something like this. We can say that is the x direction and that is the y direction. Absolutely nothing is stopping us from doing that, and that aligns with our I think it was 20-degree slope. That gives us the 20-degree slope. Okay, so we're concerned with the forces acting in this direction right here because we care about the F applied. Okay, so I'm going to say that the sum of the forces in that direction is equal to the mass times acceleration, and again the acceleration is in that direction, but we also know that it is constant velocity. Therefore, the sum of the forces in that direction is equal to 0. Okay, so now the question is, what are the actual forces? Okay, so first of all we have force applied. Okay, that is acting in our positive direction. This indicates our positive direction. Yeah. And then what other forces do we have? Okay, so we have minus force friction, definitely. And then also there's this hidden force right here. Right there, that force there, which we can say is mg, and this is the value of theta. This is also theta. Mg, we're looking for sine theta. So minus mg sine theta is equal to 0. So I'm going to say that the force applied is equal to 21. Was it 21? Yeah, it was 21. 1, 2, 3 plus 205,800. Sine of our angle is 20, and so our force applied is given as 91,387.75 units of newtons because it's a force. Okay, cool stuff. So not too difficult, and that is our final answer. Okay, looking at the next question. Okay, 5.2.3. Okay, I know this is a bit of a mess with me doing it everywhere, but I will figure out a better system. But I don't think it's too hard to follow. So calculate the output power of the engine of the motor. So what is our formula for power? Power is equal to a force times a velocity. Okay, and what force is that? That is not the net force, but rather the applied force. Okay, and we already calculated our applied force as being equal to 91,387,75. And what is our velocity? Well, it was given to us right over here because it's constant, times 1.4. And so the answer that we get is 127,942,84. And what units do we have for power? It is watts. And there we go, there's our answer. Okay, then the question says 5.2.4. Explain why the work done by the cable on the carriage between the bottom and the top of the slope is greater than the gain in potential energy. Okay, so what is the reason? There are quite a few reasons we can give. One of the reasons is we can say that some of the, we can say something like, so when we're applying the force, some of the applied force by the motor or by the cable is doing work against friction. So basically, because there's friction, if there was no friction, the energy at the bottom, the height that we achieve, the actual height we get to would be much higher, would be, let's say, actual height would be greater than 8 meters. That's less than greater than 8 meters. But because of the friction, we're being brought down to 8 meters. Okay, so as a side example, what you can even do is try and figure out the height you would get to if there was no friction. Okay, but yeah, that's basically what I wanted to cover. Basically, we did all the questions. Nothing was particularly difficult. Maybe some of it you needed to think just a little bit, but yeah, I hope that helped. Yeah, and in the next video, I will be going over question 6, or potentially, I think I skipped out question 4. I did skip out question 4, maybe question 4. Okay, thanks for watching, guys.